Welcome to Linear Algebra, Chapter 5, Section 3, Applications to Linear Equations, the Rank of a Matrix. Now, you're already familiar with what the rank of a matrix is, but we find that here is what I've already been talking about, that we find there's, generally speaking, three ways to interpret the solution set to a homogeneous system of linear equations, AX equal the zero vector. So when you have a system of M equations in n unknown variables x1 through xn, the solution space, which again is a subspace of Kn, can be interpreted in one of three ways. The first way is that the solution set consists of all vectors capital X that make the linear equation x1a1 plus x2a2 plus dot 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 plus x sub n a sub n equals 0 be true, where the superscripts are the columns of the matrix, the columns, the first column, second column, dot dot dot, through the last column. Linear combinations of the columns of the matrix. That's one interpretation we've looked at before. The second interpretation that we've already considered is that the solution set to the homogeneous linear system is the orthogonal complement of the row space of A. The orthogonal complement of the row space of A. So it says here in part B that the solutions form the space that is orthogonal to the row vectors of the matrix A. What that really means is that the row space of A, the subspace of Kn, spanned or generated by the rows of the matrix. And then third, it's also the kernel of the linear mapping represented by the matrix A. And you can always think of the matrix A as being its own linear mapping going from Kn into Km. And so you see in my handwritten notes on the right side here, part A is the solutions of the linear relations among the columns of A, and part B, when we let W be the row space of A, then the solutions to AX equals 0 vector is W perp, the orthogonal complement of W, and Kn is the direct sum of W perp and W, or vice versa, W plus W perpendicular. And again, part C, when you let L sub A be the linear mapping from Kn to Km that represents the matrix A, then you find that the solutions to AX equals 0 vector is simply the kernel of L sub A. Now, theorem 3.1 is very similar to what we looked at in the previous section again, where W is a subspace of V, or in this case of Kn, and then you look at the orthogonal complement W perp, and it turns out that the dimension of W plus the dimension of the orthogonal complement equals the dimension of Kn, which is n. Now, the proof of this theorem for the matrix case is actually left to section 5.6, theorem 6.4, and we'll look at that in the next video. But here again, we're simply applying the very same theorem that we've already seen several times already, where you have the dimension theorem, and it turns out that the rank of a matrix A is equal to two things: the dimension of the column space of A, and it's equal to the dimension of the row space of A. Now remember, the row space is a subspace of Kn, the column space is a subspace of Km, but they have the same dimension. And it's also the same as the dimension of the image of the linear mapping. So here's a very important equality. The rank of matrix A is the dimension of the column space of A equal to the dimension of the row space of A, which in turn is the same number as the dimension of the image of L sub A. So there we have it. Now also can think of the rank of A as the number of linearly independent rows of A, or the number of linearly independent columns in the matrix A. I'm going to look at three examples, and homework 11 is there on page 117, 118, 1H, 4C, and number 7. And there's a little hint here for number 7. Number 7 is the matrix version of homework 6, number 4. So take that hint to heart, because it will help you for number 7 for homework number 11. Now let's look at example 1. It's on page 115 of our textbook. Example number 1, finding the rank of a matrix. Well, all you do to find the rank of a matrix is row reduce it to reduced row echelon form. Here's the example: 2, 1, 1, 0, 1, negative 1. Find the rank of this 2 by 3 matrix. Okay, so all we do is row reduce it to reduced row echelon form, and you see what you get there on the right hand side: 1, 0, 1, 0, 1, negative 1. And as a general rule, the rank of the matrix is equal to the number of non-zero rows in the row reduced echelon form. So since both of our rows reduced to non-zero rows, the rank of this matrix is equal to 2. Now you can also see that 2 is the number of linearly independent rows, but if you look carefully at the columns of the row reduced form, the first column is E1, 1, 0. The second column is E2, 0, 1. The third column is a non-elementary column. E1 is an elementary vector, E2 is an elementary vector. Remember, a vector is elementary if it only has one 1 and all the other entries are 0. Non-elementary is anything else. So the third column is non-elementary, which means that the third column is dependent on the first 2 columns. So we can see that the first 2 columns are linearly independent, and the third column is dependent on the first and second columns. And so the number of linearly independent rows is equal to the number of linearly independent columns, which again is equal to 2. Or you can also use the dimension theorem to identify the rank of the matrix. Now, if you look at this as a homogeneous linear system, for example, and you look at the kernel of A, where you have 3 variables, x, y, and z, looking at the row reduced form, again, the third column, the z column, is, now I said a moment ago that the third column is linearly dependent on the first and second columns, that's true. But that means that the variable z is going to be an independent parameter. And when you're looking for the parameters for the solution set of a homogeneous linear system, you're actually identifying the non-elementary columns or repeated elementary columns. So the z variable will be an independent parameter, and it has only one parameter. And so the kernel of this matrix A has dimension one parameter. And then if you look at your dimension theorem, it's a 2 by 3 matrix, which means the mapping goes just the opposite from R3 to R2. Dimension of R3 is the dimension of the kernel of A plus the dimension of the image of A. So 3 is equal to 1 plus blank. Well, fill in the blank. The dimension of the image has to be 2. And that's equal to the rank of the matrix. The rank of the matrix. Now, on the next page of our text, 116, example number 2, and I work it just a little bit differently to the text. It says to find the dimension of the solution set to the following system of equations. Find the dimension of the solution set. We have 2x plus y plus z equal to 1, and then y minus z is equal to 0. Okay? Well, form the augmented matrix whose rows are 2, 1, 1, augment 1, and 0, 1, negative 1, augment 0. Row reduce it. You see what you get. 1, 0, 1, 1 half, 0, 1, negative 1, 0. And we have our 3 columns with our 3 variables, x, y, and z. And so we clearly see that z is the independent parameter. So let z equal, say, the parameter t. And then from the second equation, we see that y is equal to z, which is equal to t. And from the first equation, that x is equal to 1 half minus z. So x is 1 half minus the parameter t. So one way of writing the solution set would be the solution set S is the set of ordered triples having this format: 1 half minus t, comma, t, comma, t, where t is any real number including 0. Now, my second line there says, let S be SP plus SH. Now, this is coming from the theorem we did a few weeks ago that says that the solution set to a non-homogeneous linear system, AX equal B, is equal to a particular solution plus the solution set to the associated homogeneous linear system. So P stands for particular solution, H stands for homogeneous solution set. Now, the particular solution I always use is the one where I'm going to set the parameter t equal to 0. If I set t to be 0, then one particular solution is the ordered triple, 1 half, comma, 0, comma, 0. Okay? Now, if you take the same row reduced matrix, 1, 0, 1, 0, 1, negative 1, augment with 0, 0 rather than 1 half 0, and then look at the solution set for the associated homogeneous linear system, you'll see that x is equal to negative z, or negative t, and again y is equal to t, and z is equal to t. So the homogeneous linear system has solution negative t, comma t, comma t. Factor out the t, and then you have the following format. You have the fixed vector 1/2, 0, 0 plus t times the vector negative 1, 1, 1. That is the format for a straight line going through the origin in R3. That's a line going through the origin in R3. And of course, it has dimension 1. Dimension 1. And then example 3, also here on page 116, is what is the basis for the space of the solution set of this one system, this one equation, this one linear equation. 3x minus 2y plus z equal 0. Well, I only have one equation. So I can solve that equation for x or for y or for z. I typically solve it for z. So solve the one equation for z. You'll notice that z is negative 3x plus 2y. Now, my solution is very quick and simple. The textbook solution goes in a different direction that I don't really care to go into. So look at my handwritten solution. The solution set, call it S. Now notice now there's two parameters. Let x be S, parameter S. Let y be parameter t. Two parameters. That gives me the clue that the basis will have two vectors. Any basis will have two vectors. So the solution set S is the set of ordered triples S, comma, t, comma, negative 3s plus 2t. Now, to find two basis vectors, here's what I do. Now, this is not unique. You can choose other numbers, but this is the most elementary basis that you can find. When you have two parameters like s and t, first, let s equal 1, and then let t be 0, and then second, let s equal 0, and let t equal 1. So in the first case, we let s be 1 and t be 0, we'll get the vector 1, 0, negative 3. Second, if we let s be 0 and let t be 1, we get the vector 0, 1, 2. That means that those two vectors, namely 1, 0, negative 3, and 0, 1, 2, form a basis for the solution set. Certainly, it's not the only one. There's infinitely many bases for the solution set, but this is the easiest and most simple one to find. Now, again, the textbook did something different and got a different basis, but I think what I did is the easiest and quickest way to see it. And so that's really all there is to section 5.3. So I'll see you next time. Okay.